This video will cover unanalyzed elements and the various options for accounting for them in Probe for EPMA. Because of effects like electron backscatter and X-ray absorption, accurate matrix corrections are vital for accurate analyses. So we're kind of stuck in a situation where we have to know what's in our sample to know what's in our sample. The ideal solution might be to measure every element in the sample for quantification, but of course this is not always practical or even possible. For example, some light elements like lithium in borate beads or beryllium in beryl can't be measured. And of course, the most obvious and familiar case is oxygen. Rarely is it measured in EPMA analyses as it's not particularly easy to measure, but thankfully it has a well-defined stoichiometric relationship for most elements, so it's almost always simply calculated. The same concept would be valid for carbon in carbonates or carbides and nitrogen in nitrates or nitrides. Another circumstance where measuring all the elements may not be ideal is when we're maximizing counting time for trace elements or mapping and our spectrometer configuration might be limiting. For example, if you're trying to measure titanium with as many spectrometers as possible while counting simultaneously, any elements we can skip measuring means more time on our trace elements of interest. This is especially advantageous in simple matrices like carbonates, quartz, zircon, as well as alloys or synthetic materials. This even has potential in more complicated matrices like feldspar, garnets, pyroxenes, or anything where the host material has at least a limited range of compositions that is known or could be quantified in advance. So this video will address specifying concentrations for spot analyses, but also note that these same options are available in CalcImage for quantitative element maps as well, where minimizing count time is really essential. So how do we go about specifying concentrations in PFE? The options can be found in the Analyze window. If you don't have that open already, that's going to be that button there. It'll bring up this dialog. And the options for specifying various elements are going to be in Calculation Options here, as well as Specify Concentrations here. Okay, and we'll show some examples of each as we go along. Now, before we can specify a concentration, we're going to need to tell the software that that element exists. So let's use this calcite sample as an example. So if I hit Analyze here, you can see that our total is low, about 53.5%, give or take. And that's because we have only measured calcium as a major element here, and we are not accounting for the carbonate in our calcium carbonate in our calcite. So it's missing a large portion of the matrix in its correction. So what we're going to do is we need to add carbon to our element list. So we're going to hit elements cations. We're going to come down here and hit an empty row. We're going to type in our element, and it's now trying to pull it up from EDS because obviously we analyzed this sample already, so we can't go back in time and put it in with WDS. By the way, this EDS WDS combined analyses is a great feature of PFE, though it's beyond the scope of this. But we want to specify it. Now, unfortunately, for some reason, you cannot click specify here. You have to go in. PFE thinks it's trying to measure the K alpha line. So you have to go into the X-ray line, pull down here, scroll all the way to the bottom, and click on this empty line. And now it knows it's specified. So we're going to hit OK, and now we have carbon in our list, and hit OK again. And now you can see that we have our carbon in our list. And so we're going to go back into calculation options here. And now we want to do element by difference as an oxide formula. And we're going to select carbon from our list right here. And we're going to check that box. And what these two by difference, I'll show you this one in just a second, but what the by difference is doing is it's basically going to say, okay, I have a total of 55%. Whatever remains up to 100% is going to be the specified elements oxide formula. So we're going to hit OK. And now you'll see, so remember we had about a 53.5% total for calcium oxide there. When we hit analyze, now it's going to add that carbon as specified. And there's our CO2, and we have 100% total, but now notice that we are at 55.2. So we had a over 2 weight percent, or approximately 2 weight percent difference without the proper matrix correction. So that was error that we introduced by not having a proper matrix correction, and fairly substantial, 2 or 3% relative. Now, when we use the by difference, again, it gives us this exactly 100% total. Let's just demonstrate the other one here. So I'm going to go to the LITET bead. We're going to hit analyze, and you'll see in our list we don't have any lithium or boron for our lithium tetraborate, and we've got this very low total. So I'm going to go into calculation options, and rather than add the elements to the list and do element by difference, because in this case we have two elements that we've got to account for, we can actually use this formula by difference. So we know we've added the lithium tetraborate, and this is cool that it's just got this as an example. So we're going to add our lithium 2, boron 4, oxygen 7. Calculate the formula by difference. And what's nice about this is that it will actually, we don't have to add those elements. It's going to add them for us to the list when we hit analyze. So now I've said take up the remainder, 60 some percent of the total here, and make it lithium tetraborate. So now when I hit analyze, you're going to see that there's our boron and lithium. And now we've got our 100% total, and we've got a much more accurate matrix correction because we've accounted for that lithium and that boron. And as you can see, it automatically added them to the list. Now the by difference route is very convenient, and depending on what you're specifying, sometimes it's the only option if you don't have some sort of a stoichiometric relationship. But it can obscure other analytical issues because it always results in this perfect 100% total. So if there's a problem with the analysis resulting in an artificially low or high total, you won't be able to spot it with the by difference calculations. So what we can do is, let's go back to our calcite example here, is we can actually use stoichiometric relationships to another element to specify. And sometimes this works better, as I said, in case you have some issues with other analytes. So if we go into calculation options, we had element by difference as carbon, but in this case, now we're going to go down here to this stoichiometry to another element. So since we know this is a carbonate, a calcium carbonate, we can say that we want one atom of carbon to one atom of calcium. And now when we hit OK and we hit analyze, now the results are going to be very similar for this because this is a good analysis, but you can see now that we don't have this perfect total, and clearly here I've got a little bit of a low total for some reason. But what it's basically done is it says, well, I found this many calciums. I'm going to take that, make an equal number of carbonates, and add the oxygen to it, and do this stoichiometric relationship. So I prefer to use this method when possible if you do have an element that has got a good stoichiometric relationship. It's actually can be handy as well. I once rescued an overnight mapping run where the user had accidentally failed to include aluminum in their element list for a garnet map, and I was actually able to use this stoichiometry to another element to rescue this analysis. So what I did is I took a few shots, spot analyses on the garnet, measured the silica and aluminum ratio, noted that it didn't change very much on that particular garnet. And so I was able to actually specify silica, use silica to specify aluminum to get the correct matrix correction for that map without having to do another 24-hour overnight run just to collect the aluminum that had been missed. No, that's not perfect. It's certainly preferable to running another set of maps and can be really pretty handy feature. Lastly, we're going to look at some of the options for specifying concentrations from the specified concentrations dialog. So when we open this dialog, we've got some options here to choose from. We could load a standard composition, so you could pick any one of these and load the composition by clicking this button, and it will load the appropriate elements. Anything you haven't analyzed will be loaded into the list, and those elements will have the same concentration as the standard. We could specify by another analysis. So if we've analyzed some standards or unknowns that we want to use as our specified concentration, for instance, say you have something where you're measuring trace elements in a mineral, and what you could potentially do is go and do a series of analyses out of that mineral to get an average composition that you could then specify from that analysis, and it would add those elements, and then you could measure, for instance, your trace elements without measuring the major elements. This would be good for mapping purposes as well. And then lastly is this specified by unknown sample. This is very similar to this. The only difference is it will not add any concentrations for elements that have not been calculated already, such as something in the calculation options dialog. In this case, if you had that, this is basically the same as hitting the analyze button and calculating all of those concentrations and then adding them to the list over here. So how is this useful? Let's take a look at our serpentine sample here. So we've measured this sample, and we're obviously going to get a pretty low total because it's got a lot of water in it that we have not accounted for. So for instance, you're measuring a mineral that maybe you've used FTIR or some other method to get CO2 or to get water content. You can then specify that based on this specified concentrations. So in this case, we've got our serpentine. We're going to open this up. We've added H to our list using our elements cations already. So I can do this by oxide or elemental percent. We're going to do by oxide. So we're going to type in the water content here, and that is 14.73. And now when we hit OK, it's going to add that in and hit OK again, and now that is part of our list for our matrix correction. And just to see what kind of difference, we've got 38.9 and 35.9 for silica and magnesium. So now we're going to hit analyze, and we'll see how much that matrix correction affects that. So a couple, what have we got? Over 0.5% there and 0.5% there of error that we've eliminated just by specifying that H2O. So hopefully that helps you understand the specified concentrations and some of the reasons that you would want to use them. And thanks for watching.